Yeah, thank you everyone for coming. I see a lot of familiar faces. So today I'll talk about from transparent to confidential, the next frontier. All right, so there's one thing in common. There's one thing that all these blockchains have in common today, is that they are completely transparent databases. But what we believe is that fundamentally you need a minimum confidentiality in order to get any mass adoption in blockchain. A couple examples, right? So who here has crypto in a wallet? Okay, the majority of us. If you actually want to use crypto as your bank account, there's no way this is practical today, right? You can see your neighbor's balance, your friend's balance. So you need to be able to hide information in order for crypto to become your bank account or payroll. Second, institutions and enterprises are still having a hard time entering the space because they need a minimum confidentiality, right? They have trade secrets, they have revenues. And lastly, there are just a lot of use cases that wouldn't make sense without any confidentiality, such as like poker, right? And so we believe that blockchains will have its own SSL moment. So if you think about the early internet when it was just HTTP, you couldn't do much, right? You could do maybe academic research, a simple networking between your friends, but you really needed SSL to start encrypting the internet and do things like payments, healthcare, all sorts of practical use cases on the internet. And so this is kind of the same thing with blockchains. We are deeply limited by practical applications to bring in really Web2 use cases to Web3 because there's no confidentiality. So we believe that blockchains will have its SSL moment, and this is what Inco is building towards. So we see ourselves as the confidential compute layer for existing blockchains. We see ourselves as a separate layer. Just you have folks like Celestia building DA as a layer. We're the confidential compute layer. And so the way that we do this is by introducing new data types, operations to the EVM. So we do this by leveraging advanced techniques such as FHE, MPC, ZK, and TEE. And what you get with this is having this idea of private state that's fully on-chain, but not only you can store private state on-chain, you can also do state transformation via these different operations. And you don't need to build anything off-chain anymore, right? A lot of the applications today still spend a good amount of time building all sorts of privacy infra off-chain just to enable all of these use cases. You can just bring all these things directly on-chain. So we offer the most intuitive way for builders to basically build these new use cases in the simplest way. So first of all, this is all going to be in Solidity. You get to deploy this Solidity code on top of existing blockchains. Second, this means that you can tap into existing user base. So we're not saying, hey, you should come to a new different blockchain. We're saying we'll meet you halfway and just build there. And then lastly, you can also tap into existing TVL by proxy. And I would say if you're a builder interested in building newer use cases, definitely I'll say this is probably the easiest way for you to get started. And so roughly speaking, our category is what we call the encryption-based solutions. So there's roughly two broad privacy categories today. So one is commitment-based techniques, so ZK mostly. And the second category is what we call encryption-based solutions, so MPC, FHE, TEE. And they have quite differentiated properties here. So I'll just highlight a couple ones that I think are interesting. So ZK is actually very interesting because you could argue it's actually more private than something like MPC or FHE because every single user has their own private key inside the wallet. So the secret actually never leaves the wallet, never leaves the client side. However, on the MPC side, FHE side, you have to basically trust this MPC network to do decryptions on your behalf. So you can argue it's less private, but what you gain really is this idea of composability that Tasio earlier also mentioned, that is quite necessary and useful in crypto. So why is composability such an important property in crypto? So if you think about how everything involved in crypto, something like an ERC20 is the basic primitive that is used everywhere. For trading like Uniswap, lending like Aave, or you can also do governance with this. And so basically people are used to building on top of each other's primitives, and that's how you create network effects, a whole ecosystem within a EVM. So confidential ERC20 as an example, because it has this ability to compose, you can also think of this extending to, let's say, private payments, private voting, or private lending. So in sum, this is really kind of like the magic of this idea of a shared state or shared private state. So we published this paper with Circle Research a few months ago around proposing this new standard called confidential ERC20 framework. The couple findings here that were interesting, one is using a encryption-based approach, you have this very flexible way to program logic to decrypt. And so I mentioned earlier, with ZK, what you get is enhanced privacy. The downside is, typically when you do a private transfer using ZK, you have to specify the recipient's viewing key during the proof generation ahead of time. So this makes it very rigid for you to program additional decryption logics. Versus something that's more encryption-based, all these decryption logics are fully on-chain, so you can always change the decryption logic after the fact, right, via transaction, governance, et cetera. So this makes it very easy for businesses to program any business logic, risk management, and compliance. The second part is composability, so folks can build on top of this standard, such as DeFi or other applications. And lastly, this idea of programmable transfer rules is also quite interesting because if you have on-chain identity that's also encrypted, you can also program any sorts of transfer rules. So let's say I'm based in Europe, someone else is based in the US, and they're not allowed to transfer money to each other, right? So you can actually, without revealing where they're actually from, determine whether or not you're allowed to do this transfer. From a high level, confidential ERC20 is very similar to a regular ERC20. Instead of a mapping of address to uint, it's a mapping of address to euint, this new data type. And when you do a confidential transfer, you're basically hiding the specific amount that you're sending out. So it's different from Tornado Cash, where you are breaking the linkage between sender and recipients. Here, you are only hiding specific metadata here, which is the amount. In our case, we're using FHE as an example here, where as you transfer a confidential amount, you have to check whether or not this amount is less than user balance, right? So using FHE, you can do a homomorphic comparison, and then using that logic, then determine whether or not this transfer should pass through. Another example that I mentioned earlier, it's crazy that in crypto, we still don't have fully on-chain poker. This is because poker is a bluffing game. You need hidden information. So with things like FHE, you have OPRF, you have ways to generate on-chain randomness. So here we basically generate the cards on-chain, and then you can build this game on Base, for example. This is one of the first use cases we built internally a year and a half ago. Who here knows the game Mafia? Okay, it's a bluffing game, right? You have a secret killer, you have a doctor and a detective. So you have to be able to hide information on chain. So we actually won the ETH Global NYC hackathon because it was a very novel experience that did not exist in crypto before. And so again, a lot of the things that we do here, the reason why we believe this is the next iteration of blockchains is because you need to hide information for very basic use cases that are very practical. In terms of DeFi, one interesting thing we noticed is that if you build something on the private AMM, you also get MEV protection by default, right? So if people cannot tell how much you're swapping, they can refund run your sandwich attack you. Private voting is another very interesting example of why this idea of composability and shared state is very important. Today, if you were to write a private voting application in ZK, it is a multi-party use case in which you have to basically do a lot of off-chain coordination and eventually still trust some kind of a centralized prover to do the tally, which could leak information. With something that's encryption-based, it's very simple, right? People cast directly their choice onto the smart contract, and you do the state transition directly. So really, this presentation really is to drive the point that, in my opinion, there's only two problems that are not quite solved in terms of infra in crypto. One is interop, so chain abstraction, be able to spend money from one chain across multiple chains. The second one is really around privacy. It's really a problem that, generally speaking, is still very fragmented and still unsolved. And like we said earlier, it's very necessary for mass adoption to have a minimum amount of confidentiality. And with this, we can enable all sorts of new use cases that doesn't exist in the blockchain space. So we are compatible with existing Ethereum tooling, so you can get started pretty quickly with Ethereum, MetaMask, Solidity, also Remix, and Hard Hat. So yeah, definitely. We have an internal testnet right now called Rivest. So it is an internal devnet on a private chain, but you can already trial these experiences and experiment with this idea of private states. Yep. Thank you, everyone.